Our speaker today is Shuxing from Simon Fraser University in Canada, and he will be talking on packings of partial difference sets. Thank you, Shuxing, and the floor is yours.
Thank you, Sandra. Thank you for the invitation, and I feel honored to give this talk today to the New York Combinatorics seminar. My topic is packings of partial different set. My research is supported by the Pacific Institute for the Mathematical Sciences, and this is joint work with my host, Jonathan Jedwab from Simon Fraser University. So first of all, I will explain how partial difference set being a underlying configuration explaining many two-valued phenomenon in many different mathematical areas. So let me just start with one simple example. We are looking at the graph 5 cycle. And this graph is an instance of the so-called strongly regular graph. So for a strongly regular graph, you see exactly two different numbers of the common neighbors. For example, you pick up two incident vertices in the graph. Then they necessarily have zero common neighbors. And if you pick up two non-incident vertices, they have exactly one common neighbor. So for this strongly regular graph, we are looking at a two-valued phenomenon. So given a pair of vertices, number of common neighbors takes only two values. And indeed, we can reinterpret this two-valued phenomenon using something else. So for example, we can label the vertices of the 5 vertices using the 5 elements in Z5. And we pick up subset D of size 2 from the group G. Now I'm claiming the subset D actually tells me how to reproduce this C5. So for example, if I take the vertices 0 and 1, there are two differences generated from them. 0 minus 1 is 4 in the group Z5, and 1 minus 0 is 1 in Z5. So the two differences are 1 and 4. Notice that 1 and 4 belongs to the subset D. Both of them belong to subset D. So in that case, we just draw an edge between 0 and 1. They are incident. On the other hand, if we pick up 0 and 2, then we do the same thing. There are two differences, 2 and 3, generated from them. In this case, 2 and 3 are not part of the subset D, so we do not draw an edge between them. They are non-incident. So by using a group G and a proper subset D, I can recover this C5 in the way I just mentioned. So so the natural question is, can we find out the counterpart of the two-valued property in terms of the subset D? Actually, we can do that. So we will consider the translations of D, meaning D plus G. So we just add a group element G to the subset D. We get another set. So for those translations, I always consider the non-trivial ones, meaning the element G is not the identity, because if D plus identity, we get D itself, which is degenerate. So given the proper D and G, we look at the non-trivial translation of D intersect D itself. And this intersection has exactly two distinct sizes. And the size depends on the relation between G and D. So right here in red, we are looking at the counterpart of the two-valued phenomenon in terms of subset D. This is just the first example showing you some two-valued phenomenon can be expanded in terms of the two intersection sizes of subset D. Okay, so let's go to a second example. The second one involves projective space PG43 and the material group M11. So I'm just trying to give you some very rough idea. So it is absolutely fine if you do not know every terminology in this paragraph. Okay, so PG43, the projective space, contains 121 points. And we consider the action of the material group M11 on PG43. So this action splits the point set into 2-point orbits, O1 and O2, and they have sizes 11 and 110 respectively. So we are looking at the two-valued phenomenon again, two different orbits with different sizes. And as you can imagine, this phenomenon can also be expanded by a subset in a finite abelian subgroup, which satisfy the two intersection size property. So we can construct a subset D from the first orbit O1, and every non-trivial translation of D intersect D in two different sizes. And the size depends on the relation between G and D. So again, the two intersection property reflects the two-valued phenomenon. Okay, so that is the second example. Here is the third example, and I will not give you the full details, but just to mention, we are considering an ovoid in a projective space PG32. For this ovoid D, it satisfies a two-valued property. So we take D and intersect with all of the planes in this projective space. And the size of intersection is either 1 or 3. So again, we have two-valued phenomenon right here. It can be expanded by the intersection property as we have seen before. All right, so up to now, we introduced the 3 examples. And now we are ready to give the formal definition of partial difference set, which is the main configuration we are interested in. So for a partial difference set, we work in a finite abelian group of order V, and the set itself is a K subset of G. The defining property is what we just saw, D translation, any non-trivial translation of D intersect D in two different sizes. And if D satisfies this property, we call it a VK lambda mu partial difference set, or in short, PDS in G. So there are 4 parameters for a partial difference set, and let me recap their meanings. So the first parameter V is the order of the finite abelian group. Second parameter K is the size of the subset D. And third and fourth lambda is the intersection numbers. So that is the formal definition. And you may wonder why we call this object a partial difference set. How is it related to difference? Actually, we have an alternative definition. So given a PDS D, we take the multiset, we X minus Y. Well, X, Y are all the distinct pairs from D. If we look at this multiset, we shall see that every element of D occurs exactly lambda times in the multiset. And every non-identity element outside of D occurs exactly mu times in it. So we can rephrase the partial difference property in terms of difference. So from now on, we will assume that the identity element is not in the PDSD. And there are many examples of PDS related to subgroups. So given a group G and a subgroup H, if we take H minus the identity, we will get a PDS. So it is an easy exercise to verify H minus identity is a PDS. And this type of PDS is somewhat trivial. So we call it trivial PDS. Of course, we are interested in the non-trivial PDS. Okay. Hopefully, I have explained why PDS is interesting, because PDS is the underlying object expanding meaning to value phenomenon in various mathematical areas. For example, in graph theory, the 5-cycle example, or more generally, the strongly regular graph. In the permutation group, well, in the second example, we see the action of material group on projective space. And also in finite geometry, we see the all void in PG 3.2, and actually in many other areas. So up to now, I explained why partial difference set is interesting. Next, I will introduce a character approach to deal with partial difference set. So let me first give you an example about characters. So in the group G, 2 cross 5, every element of G induces a character acting on the group G. So we denote the character as chi sub AB. And for example, chi sub 1, 3 is the character induced by the element 1, 3. And we can apply this chi to any element of the group, for example, 1, 2, and compute this character value. In the end, we will get a 10th root of unity. So why we get 10th of unity? Because we are working in a group with exponent 10. The exponent of group determines what we will get in the end. So the computation is fairly straightforward. So we can, given any character, we can easily compute chi of some group elements. Indeed, every character induces a group isomorphism between the group and the set of, in this case, 10th root of unity. So that is a group isomorphism, preserve a lot of information of the group. Indeed, there's one special character called principal character. This one is induced by the identity element of the group. So the principal character maps everything in the group to the number 1. So somehow this principal character is sort of boring because it is a constant function. And for all the other characters, we call them as non-principal. So in the rest of talk, we will mostly focus on the non-principal characters. A side note about the characters is that if we collect the set of all characters induced by G, we actually have another group called character group. And this character group is isomorphic to G. So the characters form another nice algebraic configuration. Okay, so this is the example of character. And how are we going to use characters to study partial difference set? We would like to record a classical result by Turing back to 1965. So we worked in a group G with exponent n, and D is a subset of G. Pick up any character chi, we can apply that character to the subset D. So we just apply chi to every element in D and sum all the values up. So indeed, this chi of D is just a summation of nth complex root of unity. So we have n roots of unity because the exponent is n. So Turing's result tells us the subset D and the sequence of character values of D, they carry same amount of information. So if you know one thing, you know the other immediately. Actually, if we know the subset D, as we mentioned before, computing its character values is no problem. So from left to right is easy. The non-trivial part of Turing's result is we can start from right-hand side and recover the left. So we just start from the sequence of character values, and we can recover the set itself. The advantage of this observation is that instead of dealing with a subset in groups, we can deal with a sequence of complex numbers, which might be a lot more easier than dealing with D itself. So Turing results supplies the major tool to study a partial difference set. We will just look at its character values. Okay, so let me give you an example. Well, it is given G and a subgroup H. H minus identity is the trivial PDS. Let's just look at the character value of the trivial PDS. And necessarily, you will see two different integral values, either the size of H minus 1 or minus 1. And the value depends on whether chi is principal on H or not. So chi principal on H means chi maps every element of H to 1. So indeed, we are looking at a two-valued phenomenon again. Oh, I'm sorry. We are looking at a two-valued phenomenon right here again. And this phenomenon is in the character land. So in general, given any partial difference set, we necessarily have two distinct integral character values. That is the defining property of a PDS. Okay, and now let me give you a non-trivial PDS. So in 3x3, we can construct a non-trivial PDS, and we shall see two distinct character values. In this case, they are -2 and 1. Okay. So so far, I have introduced the character approach to partial difference set. And we are mainly interested in a subclass of partial difference set named the Lotting square type PDS. So the Lotting square PDS is just a PDS whose parameters satisfy this special form. And actually, the parameters of Lotting square PDS can be determined by two numbers, n and r. So recall that a PDS has 4 parameters, and we have one relation among those 4 parameters. So effectively, we need 3 numbers to determine the parameter of a PDS. However, for the Lotting square type PDS, we only need 2 parameters, only need 2 numbers, n and r, to determine all 4 parameters. So that is a one reason why Lotting square PDS is nice, because it is simple in terms of the numbers determine the parameters. Okay, and with no surprise, we can describe Lotting square type PDS in the language of characters. D is a NR Lotting square type PDS if D has the right size, and when we apply non-principal character to D, we see 2 distinct integers, -r or n minus r. Okay, so in fact, the previous example is a 3-2 Lotting square PDS in G. You can verify this by plug in n equals 3, r equals 2 in the formula. All right. Yeah, up to now, I introduced the character approach to partial different set. And do you have any question?
Maybe I'll ask a quick question.
Yeah,
So does every strongly regular graph give rise to a PDS or
no.
no?
Actually, every strongly regular Cayley graph corresponds to a PDS. So you need the Cayley graph. Yeah,
Thank you.
yeah. That's a good question. Thank you. Um, uh, okay, now next, I will proceed to the main purpose of my talk. I'm going to talk about the construction of Latin square type PDS. So the first thing to mention is that for those construction, the structure of groups matters a lot. So for example, up to isomorphism, there are two groups of order 9, 3 by 3, or the cyclic 9. We know from our previous example, in 3 by 3, we do have Latin square type PDS. In fact, if we apply character to this subset D, we get a summation of 4 third roots of unity. And magically, all those summations end up with either -2 or 1. That is the PDS property. On the other hand, if we look at the cyclic 9, we know that there's no non-trivial PDS in this group. So we can investigate these facts using characters. We pick up any K subset D of G. By applying a non-principal character to D, we get a summation of K nice roots of unity. Because we are now working in the exponent 9 group, so we sum up the nice roots of unities. So of course, it is more unlikely to get integers because now we have nice of unity instead of third roots of unity. So it is more difficult to get integers from this summation. That explains why we do not have partial difference set in Z9. So as you may say, it is more difficult to construct PDS in group with higher exponents. Okay, so now let me explain what is our contribution. I will do it with the help of one concrete example. Let's consider all the groups of order 3 to the 10. So we know that there exists no non-trivial PDS in a cyclic 3 to the 10. On the other hand, we know that there is Latin square type PDS in the elementary abelian 3 groups, 3 to the 10. So we just draw a interval, represent all the order 3 to the 10 groups. So actually, we have dealt with two extremal cases. For the cyclic 3 to the 10, which has the highest exponent, we know there exists no non-trivial PDS. And for the elementary abelian 3 groups, which has lowest exponent, we know there is Latin square type PDS. So the big question is, what about all the other groups in between? For those groups, we have the following list. Up to isomorphism, there are 41 groups of order 3 to the 10. Among them, 8 of them are known to contain Latin square type PDS. So we have constructions on some of those groups. And indeed, those constructions are the result of continuing efforts of many researchers. So basically, up to 1990, due to the work of Marr, Bailey, and Uniker, we understand the construction in elementary abelian groups very well. And after that, people started to construct Latin square type PDS in non-elementary abelian groups. And the intensive research has lasted for more than 3 decades. So people made some progress. However, there are still many cases left open. By open, I mean there are some groups in which we haven't have a construction, and also we cannot prove this group does not contain a PDS. So for many groups of order 3 to the 10, they remain open. So our contribution to this problem is that we propose a unified elementary approach which can reproduce all the above constructions. We can do it in a unified and elementary way. And more to the point, using our approach, we can construct PDS with new parameters. So that is what we have achieved. To achieve that, we definitely need some new insight into Latin square type PDS. Our insight is, instead of considering one single PDS, we should study a much stronger configuration, which is called LP packing. So LP stands for Latin square type PDS. What is LP packing? In short, it is a collection of disjoint Latin square type PDS with nice mutual property. So an LP packing is indeed a packing of partial different set. That is the title of my talk. I'm really considering packings of partial different set. And we shall note that LP packing is a very powerful configuration in the construction of Latin square PDS. So roughly speaking, knowing one LP packing, we know a series of Latin square type PDS. So somehow constructing Latin square type PDS boils down to the construction of our LP packings. So now I will explain what is LP packing. Again, let's start with an example. In the group G, that's 3 to the 4, this group contains 10 subgroups hi, I from 0 to 9. Each subgroup has order 9, and every distinct pair of subgroups intersect trivially. So if we have such configuration, hi, I from 0 to 9, we have a spread in the group 3 to the 4. So indeed, a spread is a very nice configuration in the elementary abelian group. For example, if you take a spread and you exclude the identity from the components of the spread, then those 10 components, hi minus identity, are pairwise disjoint. And if you take the union of them, you can partition all the non-identity element of that 3 to the 4. So spread is a very elegant configuration in elementary abelian group. So we can construct our LP packing from a spread. So let's say hi is a spread in 3 to the 4. Then we just pick up one component, for example, h0. And for what remains, we take out the identity element. So we get a set of 9 members, and those 9 members form a LP packing in the group G relative to h0, the subgroup we take out at the beginning. So an LP packing satisfies the following 3 properties. First of all, each member is a Latin square type PDS. Actually, in this case, each member is a trivial PDS. So if we apply character to each of them, we will see exactly 2 integer values. Secondly, the members in LP packing are pairwise disjoint. And if we take the union of them, we partition G minus the subgroup we are relative to. And thirdly, if we apply character to those 9 members of LP packing, we only see 2 possibilities. If chi is principal on H0, we see all minus 1s. If chi is non-principal on H0, we see exactly 1, 8, and 8 minus 1s. So remember, chi of one member takes the value minus 1 or 8. So theoretically, if you consider this set, you may see arbitrary number of 8 in this set. However, for the LP packing, the members, the subset have some very nice mutual property so that you either see 0 or 1, 8 in this set. So those are the 3 defining properties for an LP packing. So to actually recap this concept, let me explain it using an array of character values. So we denote HI minus identity to be HI star. So HI star are the members of LP packing. And we just take the character values for all the members and form an array. So the LP packing property means the following 3 things. For each column, you will see exactly 2 distinct values. That is the partial difference set property. And all the members are pairwise disjoint. And if you take the union, you get G minus the subgroup H0. And thirdly, if you look at the rows of the array, when chi is principal on H0, you will see all minus 1s. When chi is non-principal on H0, you will see exactly 1, 8, and 8 minus 1s. So by looking at this array, we are sure that LP packing is much, much stronger than one single partial difference set. Basically, one partial difference set means you know the information of one single column. However, for LP packing, we have much more than that. Okay, so hopefully I explained the concept of LP packing properly. And now I will show you that given a LP packing, we can easily derive many Latin square type PDS, which is our main objective. Actually, if we have an LP packing, we just take the union of arbitrary many members from the LP packing. That will give us a Latin square type PDS. So right here, I take arbitrary B members from the LP packing and end up with a 9B Latin square type PDS. Because B can be any integer from 1 to 9. You may see one LP packing gives us many Latin square type PDS with different parameters as B ranges. Okay, so to sum up, one single LP packing leads to multiple Latin square type PDS. And in our example, we define LP packing in elementary abelian groups. However, LP packing can be defined in any P group whose order is a square. So LP packing can be defined in all those groups. Okay, so I would like to convince you that LP packing is indeed an interesting object. So recall that in the elementary abelian group, LP packing is actually equivalent to a spread. So by tweaking a spread, we can get an LP packing, and also starting from LP packing, we can get a spread. So they are equivalent concepts. notice that spread cannot be extended to groups with higher exponents because spread only exists in elementary abelian group. However, if we start from the LP packing, there is indeed a way to extend LP packing into higher exponent groups. So somehow, by tweaking the spread, we get a more extendable object. That's why we think LP packing could be a better way to understand the spread, a better object to be extended to other groups. So that is the definition of LP packing. And here comes our main theorem. This is the theorem in our paper. So in a word, we managed to construct LP packing in such groups that P to the A to the power of 2n. So we have a even number copies of the cyclic group that P to the A. And this LP packing could be relative to any subgroup whose order is the square of the whole group. So you may see our theorem is really a very general one. It gives you construction of LP packing in a class of group, and the subgroup we are relative to is very, very flexible. Okay. And more to the point, we proposed a product construction. So suppose we have LP packing in two different groups. We can compose them and get an LP packing in the direct product of those two groups. And we are relative to the direct product of U1 and U2. So this product construction can extend the rank of the groups. Combining the theorem and the product construction, we have our corollary, which is our major results. So we can construct LP packing in groups of such forms. So in each one, we can construct LP packing using our theorem. And then by employing the product construction, we can get LP packing in their direct product. Okay, so that is our major theorem. And what is the benefit of it? So recall that over the last 3 decades, people intensively worked on the construction of Latin square type PDS. However, there remains many unsettled cases. Our contribution is using the LP packings, we can derive a unified construction with only some elementary approach. And indeed, instead of one single PDS, we can construct a collection of disjoint PDS with some nice mutual property. So we managed to construct a much stronger configuration. So last but not least, through the LP packing, we can obtain Latin square PDS with some new parameters. So for instance, we can get a P7, P5 Latin square type PDS in this group. So this is one of the new PDS with new parameters. Okay, so that is what we have done via LP packing. And for the rest of the talk, I will give you a little bit more details about our main theorem, which I call it as a lifting construction. So the basic idea is we start from a LP packing in the elementary abelian group. Then we do some lifting so that we get LP packing in higher exponent group. So more generally, we will start from ZP to n, and by applying the lifting construction several times, we end up with that p to the a to the power 2n. So that is the lifting construction. Okay, so I will explain lifting construction in more details. First of all, why the lifting construction is so difficult? There are three reasons. First, to do the lifting construction, we need to maintain the PDS property. So we need to construct a collection of PDS in groups with increasing exponents. So notice that constructing one single PDS in group with higher exponent is difficult. And right here, we need to construct a collection of them. So that is the first difficult point. Secondly, for the LP packing, we need to guarantee those PDS are properly arranged inside the group. They should satisfy the disjointness. And thirdly, if we take the union of all those PDS, we should partition the whole group minus a subgroup. So the union should avoid a subgroup. So all those 3 points makes the construction very, very difficult. And how can we deal with those difficulties? We need more than one big ideas. So the first idea comes from a old work by Davis and Jedwab back to 1997. So they exploited a double lifting approach to construct something called different set. And right here, we modify their construction so that we can maintain the partial different set property. And moreover, we proposed a auxiliary configuration named LP partition. Using LP partition, we can guarantee the disjointedness and we can avoid the subgroup. So we combine two big ideas to finish the construction. So let me explain the idea in this diagram. So you will see we are dealing with LP packings and the auxiliary LP partitions. Let's say we start from an LP packing in that 3 to the 4, which can be derived from the spread in 3 to the 4. Also, we know LP partition in that 3 to the 4, which can also be derived from the spread. So on the ground level, on the elementary abelian level, we have the initial object ready. And now I do a lifting for the LP partition. I lift the LP partition to that 9 to the 4. Then combining LP partition in 9 to the 4 with the LP packing in 3 to the 4, I get my LP packing in 9 to the 4. So the idea is by doing the lifting and combining with the LP packing one level lower, we get the LP packing right here. And this procedure may continue. If we can lift the LP packing from 9 to 27, then combining LP partition in 27 and LP packing in 9, we get the LP packing in 27. So indeed, this is a double lifting procedure. And the major advantage of LP partition is that we split the LP packing into two different parts, while these two parts follows very different mechanism to do the lifting. So indeed, we combine the auxiliary LP partition idea with the double lifting idea to get what we want. Okay, so of course, and there's more potential for the lifting construction because essentially we managed to propose a mechanism which simultaneously manipulates multiple subsets while this subset satisfy some very strict restrictions. So the lifting construction managed to get what we want in a very delicate way. So we are wondering if this lifting construction can be applied to some other situation. And more to the point, we would like to see if there's more construction of LP packings in group of such form. So for our major result, we can construct LP packings in even number copies of the same cyclic group. However, we do not know many construction in the odd number copies of the cyclic group. So that is one of the most interesting open problem in this area. So that is all I want to say. Thank you so much.
Let's thank the speaker. I'll open the floor for questions and I'll turn off the recording.
Mm-hmm.